Right now, as you sit in your chair, you are hurtling through space at 600 kilometers per second. The room around you, the air in your lungs, every atom in your body is falling through an abyss so vast that human language has no word for it. This is not poetry, this is measurement. You are a passenger on a planet that orbits a star. That star orbits the center of a galaxy, and that galaxy is one of 2 trillion others, scattered across 93 billion light-years of expanding void. 2 trillion islands of light, each containing billions or even trillions of stars, each separated by distances so grotesque that they transform the concept of travel into cosmic joke. Scientists have mapped them, named them, categorized them into spirals and ellipticals and irregulars. But no human being will ever visit one. Not in your lifetime. Not in the lifetime of your species. Not even if humanity survives for 1 million years and builds ships that can approach the speed of light itself. The math is simple, brutal. Final, the nearest major galaxy to our own, Andromeda, sits 2.5 million light-years away. If you could somehow board a spacecraft that traveled at light speed, the absolute maximum velocity permitted by the laws of physics, you would arrive at Andromeda in 2.5 million years. Not 2.5 million years of your subjective experience. 2.5 million years measured by the universe itself. Every star you know would be dead. The constellations that guide sailors would be unrecognizable. Humanity, if it still existed, would have evolved into something you could not call human. This is the galaxy next door, our closest neighbor, the one we can see with the naked eye on a clear night. Beyond Andromeda, the numbers become obscene. The Virgo cluster sits 54 million light-years away. The Coma cluster stretches 320 million light-years from Earth. And at the edge of the observable universe, 13.8 billion light-years distant, galaxies recede from us faster than light itself can travel. They are escaping beyond a horizon we can never cross. What you are about to witness is not a journey. It is an inventory of everything you will never reach. A census of 2 trillion prisons, each containing hundreds of billions of stars, separated by voids that mock the very concept of travel. We will catalog them, we will measure them, we will understand exactly why we are trapped here, forever. If you are ready to confront the sheer scale of your cosmic isolation, hit that like button and subscribe. Because what comes next will destroy every fantasy you ever had about exploring the universe. Prepare yourselves, we begin. 2 trillion galaxies. Let that number sit in your skull for a moment. Not 2,000, not 2 million. 2 trillion separate island universes scattered across observable space like grains of sand on a beach that stretches beyond every horizon you can imagine. The number comes from a study published in 2016 by Christopher Consolis and his team at the University of Nottingham. They didn't just point a telescope at the sky and count, they took deep space images from the Hubble Space Telescope and painstakingly converted them into 3-dimensional maps. They measured the number of galaxies at different epochs in the universe's history. They used mathematical models to infer the existence of galaxies that current telescopes cannot observe. Their conclusion shattered previous estimates. Before Consolisi's work, astronomers believed the observable universe contained approximately 200 billion galaxies. The new research showed that estimate was at least 10 times too low. 10 times. The universe suddenly became 10 times more crowded than we thought. Except crowded is the wrong word entirely. Because even with 2 trillion galaxies, the universe remains mostly empty, mostly void, mostly nothing. Here is what 2 trillion actually means. If you started counting right now, 1 galaxy per second, never sleeping, never stopping, never pausing to eat or breathe, it would take you 63,000 years to count them all. 63,000 years of saying numbers. 1, 2, 3, 4. Your great-great-great-grandchildren, born 2,000 generations from now, would still be counting. The pyramids would be dust. The continents would have drifted into new configurations. And you would only be halfway done. But even 2 trillion is conservative. Some researchers believe the true number could be 6 trillion, or 20 trillion. Because the farther we look into space, the more we realize how much we cannot see. Every time we build a more sensitive telescope, we find galaxies we missed before. Faint ones. Small ones. Dwarf galaxies containing only 10 million stars instead of hundreds of billions. The James Webb Space Telescope, launched in 2021, has already begun revealing galaxies that the Hubble could not detect. Ancient systems that formed when the universe was less than 3% of its current age. Each discovery raises the same disturbing question: if we keep finding galaxies we missed, how many more are out there beyond the limits of our instruments? How many are too faint, too distant, too small for us to ever detect? The answer is mathematical and merciless. 90% of the galaxies in the observable universe are too faint and too far away to be seen with present-day telescopes. 90%. We can only observe 10% of what exists within the observable universe. The rest is hidden behind the veil of distance and darkness, waiting, existing, unreachable. Pamela Gay, a senior scientist at the Planetary Science Institute, put it plainly in 2024. We see, at most, 3% of the universe. 3%. The observable universe itself, that sphere of space 93 billion light-years, across from which light has had time to reach us since the Big Bang, represents only a tiny fraction of the total universe. Some models suggest the entire universe could be at least 3 times 10 to the power of 23 times larger than what we can observe. That number is so large it loses meaning. It becomes abstract, a placeholder for infinity. But let's stay with what we can observe. 2 trillion galaxies spread across 93 billion light-years. The math reveals something horrifying about distribution. The observable universe has a volume of approximately 410 nonillion cubic light-years. That is 4.22 times 10 to the power of 5 cubic gigalight-years. Divide 2 trillion galaxies across that volume, and you get an average density of roughly 5 galaxies per cubic gigalight year. But average is a lie. Galaxies do not distribute evenly. They cluster together in groups and clusters and superclusters, separated by cosmic voids where almost nothing exists. The largest known void, the Eridanus supervoid, stretches 1.8 billion light-years across. That is not a typographical error. 1.8 billion light-years of nearly empty space. A desert in the cosmos so vast that our entire local group of galaxies, containing the Milky Way, Andromeda, and 50 other systems, could fit inside it and still be lost in the emptiness. Between the voids, galaxies gather along filaments and walls that form the cosmic web. The Sloan Great Wall stretches 1.5 billion light-years long. The Luniakea supercluster, which contains our Milky Way, spans 520 million light-years and contains roughly 100,000 galaxies. We are part of that structure, a single star system inside a single galaxy, inside a supercluster that is itself just one small feature, in a web that extends across the entire observable universe. Each of those 2 trillion galaxies is a gravitationally bound collection of stars, gas, dust, and dark matter. They range in size from dwarf galaxies containing as few as 10 million stars to giant ellipticals with 1 trillion stars or more. Our Milky Way sits somewhere in the middle, a typical spiral galaxy containing between 100 billion and 400 billion stars. Somewhere in that estimate, we don't even know the precise census of our own home galaxy. The variety is staggering. Spiral galaxies like the Milky Way, with their elegant rotating arms. Elliptical galaxies, bloated and red, filled with old stars and little new formation. Irregular galaxies, chaotic and asymmetric, shaped by gravitational encounters with neighbors. Dwarf galaxies so small they could orbit larger systems like satellites. Ultra-compact dwarfs so dense that they pack billions of stars into regions only a few hundred light-years across. And every single one of them is moving. The universe is not static, it expands. Galaxies rush away from each other as space itself stretches. The more distant a galaxy, the faster it recedes. This is Hubble's law, discovered by Edwin Hubble in 1929 when he observed that light from distant galaxies was redshifted, stretched toward longer wavelengths because the galaxies were moving away. The expansion rate is approximately 70 kilometers per second per megaparsec. A megaparsec equals 3.26 million light-years. So for every 3.26 million light-years of distance, space expands at 70 kilometers per second faster. Do the math forward and something grotesque emerges. At approximately 14 billion light-years from Earth, galaxies are receding faster than the speed of light. Not because they are moving through space at that speed, but because space itself is expanding between us and them. Beyond approximately 62 billion light-years, known as the future visibility limit, objects will never enter our observable universe at any point in the infinite future. Light emitted by galaxies beyond that boundary can never reach Earth because the expansion of space carries them away faster than their light can travel toward us. They exist in a cosmic prison on the other side of a horizon we cannot cross. This means that of those 2 trillion galaxies, only a fraction will ever be theoretically observable, even if we wait forever. The number currently observable will increase by only a factor of 2.36 before dark energy's acceleration makes additional galaxies unreachable. We are living in a window of time where the universe is visible. In the distant future, as dark energy continues to accelerate expansion, civilizations arising billions of years from now will see a much emptier sky. Most galaxies will have redshifted into invisibility. The cosmic microwave background will become undetectable. Future astronomers will have no evidence of the Big Bang, no evidence of cosmic expansion. They will think they live in a small static island universe surrounded by infinite darkness. But we can still see, for now. While the window remains open, 2 trillion galaxies blazing across 93 billion light-years. Each one a realm of hundreds of billions of stars. Each one containing trillions of planets. Some of those planets rocky, some with atmospheres, some with liquid water, some perhaps with life. The numbers become pornographic in their excess. If each galaxy contains 400 billion stars and 2 trillion galaxies exist, that gives us 8 times 10 to the power of 23 stars in the observable universe. 800,000 billion stars. More stars than all the grains of sand on every beach on Earth, and current estimates suggest at least 1 planet per star, which means at least 8 times 10 to the power of 23 planets, worlds, surfaces, skies. Somewhere in that census, probability suggests other intelligences must exist. Other beings looking up at their own night sky. Other civilizations asking the same questions we ask. But the distances ensure we will never meet them, never speak to them, never know if they exist at all. The Fermi paradox asks where everyone is. The answer is simple and terrible. They are out there, separated from us by voids so vast that communication becomes physically impossible. Even if they exist, even if they are broadcasting signals, the expansion of space would redshift their messages into undetectable noise before they could reach us. We are alone not because we are unique. We are alone because the universe has grown too large for connection. This is the inventory. 2 trillion galaxies. Each one a graveyard we can observe but never visit. Each one containing billions of stars we can catalog but never reach. The cosmos has given us eyes to see infinity, and legs that cannot carry us beyond our own solar neighborhood. The next chapter reveals exactly what those galaxies contain, and why every single one of them is already dead. Every galaxy you see in the night sky is already dead. Not metaphorically dead, not poetically dead, actually dead. The light reaching your eyes left those galaxies millions or billions of years ago. You are not observing them as they exist now. You are observing their corpses, their ghosts. Light echoes from a past so distant that the stars you see have likely already exploded, collapsed, or faded into darkness. The Andromeda Galaxy, visible to the naked eye on a clear autumn night, appears as it existed 2.5 million years ago. When that light began its journey toward Earth, Your ancestors were barely recognizable as human. Australopithecus walked the African savanna. No cities existed, no agriculture, no written language. The light has been traveling through empty space while your entire species evolved. From ape-like creatures into whatever you think you are now, and Andromeda is close. The Triangulum Galaxy sits 3 million light-years away. The light you see tonight left when your ancestors were even more primitive. The Sombrero Galaxy, 60 million light-years distant, shows itself as it appeared when dinosaurs still ruled Earth. The light departed before the asteroid impact, before the mass extinction, before mammals inherited the planet. Pushed deeper into space and the temporal displacement becomes obscene. The Virgo cluster, 54 million light-years away, appears as it existed in the Paleocene epoch. The Coma cluster, 320 million light-years distant, shows light that began traveling during the Carboniferous period, when Earth was covered in vast swamp forests that would eventually become coal. At the edge of the observable universe, 13.8 billion light-years away, we observe galaxies that formed when the universe itself was less than 5% of its current age. The light has been traveling for 13.8 billion years. Those galaxies are not there anymore. Not in that form. They have merged with other galaxies, been torn apart by gravitational interactions, or evolved into completely different structures. What we see is an image burned into light and preserved across cosmic time. You cannot observe the present state of distant galaxies. The present is inaccessible, you can only see the past. And the farther you look, the deeper into history you peer. This temporal lag creates a fundamental problem for understanding the universe. When astronomers catalog galaxies, they are cataloging different epochs simultaneously. A galaxy 10 million light-years away shows you the universe as it existed 10 million years ago. A galaxy 1 billion light-years away shows the universe as it existed 1 billion years ago. You are not looking at a single moment frozen in time. You are looking at a timeline stretched across space, with each distance representing a different era. But what exactly are you seeing? What composes these island universes scattered across the void? Start with stars. Stars are the visible component of galaxies, the burning fusion reactors that produce light we can detect across cosmic distances. Our Milky Way contains between 100 billion and 400 billion stars. The uncertainty range spans 300 billion stars, because counting them accurately is impossible. Many are too dim to detect. Others hide behind dust clouds that block optical light. Still others exist in crowded regions where individual stars blur together. Each star is a gravitationally collapsed sphere of plasma, held together by its own mass. The fusion of hydrogen into helium in stellar cores releases energy that radiates outward as light and heat. This process sustains stars for millions to trillions of years, depending on their mass. Massive stars burn through their fuel quickly, exploding as supernovae within 10 million years. Small red dwarf stars can burn for 10 trillion years, far longer than the current age of the universe. Stars cluster in different regions of galaxies depending on their age and composition. In spiral galaxies like the Milky Way, young hot blue stars concentrate in the spiral arms. Dot, where active star formation continues. Older, cooler red stars populate the galactic bulge and halo. Globular clusters, dense, spherical collections of hundreds of thousands of ancient stars, orbit in the galactic halo like satellites. But stars represent only a tiny fraction of a galaxy's total mass. Most stars contain roughly 1 solar mass of material. Multiply 400 billion stars by 1 solar mass, and you get approximately 400 billion solar masses for the Milky Way's stellar component. But the Milky Way's total mass exceeds 1 trillion solar masses. Where is the rest? Gas and dust account for some of the missing mass. The interstellar medium, the material between stars, consists primarily of hydrogen and helium gas, with trace amounts of heavier elements. This gas exists in different phases depending on temperature and density. Cold molecular clouds with temperatures around 10 Kelvin are the birthplaces of new stars. Warm neutral hydrogen at 8,000 Kelvin fills much of the galactic disk. Hot ionized plasma at 10,000 to 1 million Kelvin pervades the galactic halo and surrounds star-forming regions. Dust particles, microscopic grains of carbon, silicon, and metals, mix with the gas at a ratio of approximately 1 part dust to 100 parts gas by mass. These particles scatter and absorb starlight, making distant regions of galaxies difficult to observe in visible wavelengths. But dust also radiates energy in the infrared, creating a signature that infrared telescopes like the James Webb Space Telescope can detect. The total mass of gas and dust in the Milky Way equals approximately 10 to 20 billion solar masses. Added to the stellar mass, you reach roughly 420 billion solar masses, but the galaxy's total mass exceeds 1 trillion solar masses. More than half the mass remains unaccounted for. This is where dark matter enters. Dark matter is the invisible scaffolding that holds galaxies together. It does not emit, absorb, or reflect electromagnetic radiation of any wavelength. It cannot be seen with any telescope ever built. Its existence is inferred entirely through gravitational effects. When astronomers measure how fast stars orbit the galactic center, they find velocities that should tear the galaxy apart. Stars in the outer regions move too fast for the visible matter to hold them in orbit. Either Newtonian physics is wrong, or invisible mass exists that provides additional gravitational force. The evidence overwhelmingly supports the latter conclusion. Dark matter halos surround galaxies, extending far beyond the visible disk. These halos contain approximately 85% of a galaxy's total mass. In the Milky Way, the dark matter halo may extend 200,000 light-years from the galactic center, twice the diameter of the visible galaxy. This invisible mass determines how galaxies rotate, how they cluster together, and how they interact gravitationally with their neighbors. No one knows what dark matter is. The leading candidates include weakly interacting massive particles called WIMPs, axions, sterile neutrinos. Nates, or primordial black holes, formed in the first seconds after the Big Bang. Decades of experiments have failed to detect dark matter particles directly. Whatever it is, it dominates the mass budget of every galaxy in the universe while remaining completely invisible and undetectable except through gravity. At the center of most galaxies lurks something even stranger: supermassive black holes, gravitational singularities with masses ranging from millions to billions of solar masses. Sit at the galactic core. The Milky Way's central black hole, Sagittarius A star, contains approximately 4 million solar masses compressed into a region smaller than Mercury's orbit. This monster is relatively quiet now, consuming only small amounts of matter, but observations of its vicinity reveal stars orbiting at speeds exceeding 5,000 kilometers per second. Velocities that prove the black hole's existence beyond doubt. Some galactic black holes are not quiet. Active galactic nuclei occur when supermassive black holes actively consume material from their surroundings. Gas and dust spiral inward through an accretion disk, heating to millions of degrees and radiating enormous amounts of energy across the electromagnetic spectrum. The most luminous active galactic nuclei, called quasars, can outshine their entire host galaxy by a factor of 100 or more. Quasars were common in the early universe when galaxies were younger and gas-rich. Nearly all quasars exist at redshifts corresponding to distances of billions of light-years, meaning we observe them as they existed billions of years ago when the universe was more violent and chaotic. In the modern universe, most supermassive black holes have exhausted their fuel supplies and sit dormant, waiting. This is the anatomy of a galaxy. Hundreds of billions of stars, billions of solar masses of gas and dust, trillions of solar masses of dark matter. A supermassive black hole at the center, all bound together by gravity into a structure that can persist for billions of years. But even this description simplifies reality. Galaxies are dynamic systems undergoing constant evolution. Stars form from collapsing gas clouds at rates ranging from less than 1 solar mass per year in quiet elliptical galaxies to hundreds of solar masses per year. In violent starburst systems, massive stars explode as supernovae, dispersing heavy elements synthesized in their cores throughout the interstellar medium. These elements become incorporated into new generations of stars and planets, enriching the galaxy's chemical composition over time. Galaxies collide and merge, When two spiral galaxies interact, gravitational tides strip away their outer regions, creating long tidal tails of stars and gas that can extend hundreds of thousands of light years. The collision triggers bursts of star formation as gas clouds compress and collapse. Eventually, after hundreds of millions of years, the galaxies merge into a single larger system, often an elliptical galaxy, devoid of the spiral structure the progenitors once possessed. Our Milky Way is currently consuming smaller satellite galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way's gravity. Its stars slowly absorbed into our galactic halo. The Magellanic Clouds, two irregular galaxies visible in the southern hemisphere, orbit the Milky Way and will eventually merge with it in approximately 2.5 billion years. And in approximately 4 billion years, the Milky Way will collide with Andromeda. The two largest galaxies in the local group will merge. In a process lasting several billion years, the collision will not involve stars physically hitting each other. Stars are separated by distances too vast for direct impact. But gravitational interactions will reshape both galaxies completely. The merged system, sometimes called Milkomeda, will form a giant elliptical galaxy containing the stars of both progenitors. By that time, Earth's fate will have already been sealed. The Sun, aging into a red giant approximately 1 billion years before the collision, will have expanded beyond Earth's orbit, incinerating the planet. Whether life persists elsewhere in the solar system or escapes to other star systems becomes irrelevant. The galaxy itself undergoes transformation on a scale that makes planetary destruction trivial. This is what fills 2 trillion galaxies. Stars by the hundreds of billions. Planets by the trillions. Gas and dust and dark matter and supermassive black holes. All evolving, merging, transforming over billions of years. And all completely inaccessible. You see their light, you catalog their properties, you measure their distances and compositions, but you cannot touch them, cannot travel to them, cannot interact with them in any meaningful way. They exist as images burned into ancient light, ghosts of systems that may have already transformed into something unrecognizable or cease to exist entirely. The universe has given you a map of 2 trillion prisons, each separated by voids so vast that travel becomes physically meaningless. The next chapter reveals exactly how vast those separating voids actually are, and why they guarantee your species will die without ever leaving its cosmic neighborhood. "300,000 kilometers per second. This is the speed of light in vacuum, the universal speed limit. The maximum velocity at which information, matter, or energy can travel through space according to the laws of physics as we understand them. Nothing with mass can reach this speed. Nothing can exceed it. This is not a technological limitation. This is fundamental law written into the structure of space-time itself. At 300,000 kilometers per second, light can circle the Earth 7.5 times in 1 second. It can travel from Earth to the Moon in approximately 1.3 seconds. It can reach the Sun in 8 minutes and 20 seconds. This velocity is incomprehensibly fast by human standards, fast enough to cross entire planetary systems in hours or days. And it is pathetically, laughably, insultingly slow for crossing the distances between galaxies. Let's establish the baseline distance measurement astronomers use when discussing cosmic scale. 1 light year equals the distance light travels in 1 Julian year. Of 365.25 days. Convert that to kilometers, and you get approximately 9.46 trillion kilometers. 9.46 times 10 to the power of 12 kilometers. Write it out, and the number becomes 9,460 billion kilometers. This is the distance light, the fastest thing in the universe, travels in 1 year of continuous motion at maximum speed. And this unit, this light year, becomes the measuring stick for cosmic distance, not because it is convenient, but because using kilometers or miles produces numbers so large they become meaningless. Our Sun sits 8 light minutes from Earth. Proxima Centauri, the nearest star beyond our solar system, lies 4.25 light years away. the distance between our Sun and the nearest stellar neighbor equals approximately 40 trillion kilometers. If you could travel at 100,000 kilometers per hour, a speed no current spacecraft has achieved, the journey would take 46 million years. But we are not discussing travel to nearby stars. We are discussing travel to other galaxies. The Small Magellanic Cloud, a satellite galaxy of the Milky Way visible in the southern hemisphere, sits approximately 200,000 light-years from Earth. The light you see left that galaxy 200,000 years ago when your ancestors were Homo heidelbergensis. Anatomically, modern humans did not yet exist. The journey distance equals approximately 1.9 quintillion kilometers. 1.9 times 10 to the power of 18 kilometers. Board the fastest spacecraft ever built, the Parker Solar Probe, which achieved speeds of approximately 700,000 kilometers per hour during its closest solar approach. At this velocity, traveling to the Small Magellanic Cloud would require approximately 308 million years. 308 million years of continuous flight with no stops, no deceleration, no course corrections. You would depart now and arrive sometime in the Permian period of Earth's distant past if you traveled backward through time. Or in a future so distant that the continents would have completely reconfigured if time moved forward. But the Small Magellanic Cloud is essentially in our galactic neighborhood, a suburb, a nearby settlement. Andromeda, the nearest major galaxy, sits 2.5 million light-years away. The distance equals approximately 2.4 times 10 to the power of 19 kilometers. 24 quintillion kilometers. If you traveled at the Parker Solar Probe's maximum speed, the journey would require 3.8 billion years. 3.8 billion years. The Earth itself is only 4.5 billion years old. You would need to travel longer than multicellular life has existed on Earth. The Sun will have already entered its red giant phase and destroyed the inner solar system long before you reached halfway. Push deeper into space and the numbers become pornographic in their cruelty. The Virgo cluster sits 54 million light-years distant. The journey at current maximum spacecraft velocity would require approximately 77 billion years. The universe itself is only 13.8 billion years old. You would need to travel 5.5 times longer than the universe has existed to reach the Virgo cluster. The Coma cluster, 320 million light-years away, would require 460 billion years. The Hydra Centaurus supercluster, 700 million light-years distant, would take approximately 1 trillion years. 1 trillion years of continuous travel at the fastest speed humanity has ever achieved. And none of this accounts for the fact that you cannot actually travel at 700,000 kilometers per hour for billions of years. You need fuel. You need course corrections. You need to decelerate when approaching your destination. Every kilogram of fuel you carry increases the total mass you must accelerate, requiring more fuel, creating an exponential problem that rapidly becomes unsolvable. But let's be generous. Let's imagine some future civilization develops propulsion technology that allows sustained travel at 10% the speed of light. 30,000 kilometers per second, 1/10 of the cosmic speed limit. This would represent a technological achievement, orders of magnitude beyond anything currently possible, requiring energy outputs and engineering capabilities that dwarf our current civilization's total technological capacity. At 10% light speed, the journey to Andromeda would require 25 million years. The journey to the Virgo cluster would require 540 million years. The journey to the edge of the observable universe would require 138 billion years. These timescales exceed the stellar lifespans of most stars. They exceed the timeframes during which planets remain habitable. They exceed the duration that any biological organism could survive, even with perfect suspended animation. They approach and surpass the timescales on which galaxies themselves evolve and merge. You are not traveling to other galaxies. You are attempting to cross voids so vast that the concept of journey becomes meaningless. But the situation is worse, much worse, because the universe is expanding. Hubble's law states that galaxies recede from each other at velocities proportional to their distance. The current best estimate for the Hubble constant is approximately 70 kilometers per second per megaparsec. a megaparsec equals 3.26 million light-years. So for every 3.26 million light-years of distance, space expands at an additional 70 kilometers per second. Andromeda, at 2.5 million light-years, sits within the range where local gravitational effects dominate over cosmic expansion. The Milky Way and Andromeda are actually falling toward each other due to mutual gravitational attraction, which is why they will collide in approximately 4 billion years. But beyond the local group, expansion dominates. The Virgo cluster, 54 million light-years away, recedes at approximately 1,160 kilometers per second. Due to cosmic expansion. Not because it is moving through space at that velocity, but because space itself is expanding between us and it. If you launched a spacecraft toward the Virgo cluster traveling at 10% light speed, the cluster would be receding at approximately 3.9% light speed. Your net approach velocity would be only 6.1% light speed, extending the journey time from 540 million years to 885 million years. At greater distances, the effect becomes catastrophic. Galaxies approximately 4.2 billion light-years away recede at exactly the speed of light due to cosmic expansion alone. You cannot catch them, even if you traveled at 99.99% light speed. They would remain forever ahead of you, always receding. Just slightly faster than you could approach. Beyond approximately 14 billion light-years, galaxies recede faster than light. This does not violate special relativity because the galaxies are not moving through space faster than light. Space itself is expanding between you and them at a rate that exceeds light speed. Your spacecraft, traveling through space at sublight velocity, can never overcome the expansion. The future visibility limit sits at approximately 62 billion light-years. Light emitted by objects beyond this boundary right now will never reach Earth. No matter how long we wait, because space is expanding faster than the light can travel toward us. Those regions are causally disconnected from our location. They exist, but exist in a separate cosmic domain that we can never access, observe, or interact with. This means approximately 95% of the observable universe is already unreachable, already beyond any possible journey. The expansion of space has carried those regions beyond the cosmic horizon. They are gone. Not destroyed, not moved to another dimension, simply separated from us by expanding space that makes the distance between us and them grow faster than light can cross it. And the expansion is accelerating. Dark energy, the mysterious force that drives cosmic acceleration, causes the expansion rate to increase over time. In the distant future, even nearby galaxy clusters will accelerate beyond the cosmic horizon and disappear from view. The Virgo cluster will redshift into invisibility. The Coma cluster will vanish. Eventually, every galaxy outside our local group will recede beyond reach, leaving future civilizations to observe only the merged Milky galaxy. In a cosmos that appears empty and static, you live in a brief window of cosmic time when the universe remains partially visible and partially accessible. This window is closing, has been closing since the moment of your birth, will continue closing until the observable universe shrinks to a tiny bubble of nearby stars and nothing more. But even within the theoretically reachable volume, the journey times remain impossible for biological organisms or technological civilizations with finite lifespans. Consider a thought experiment. Suppose you board a spacecraft capable of traveling at 99.99% the speed of light. This represents the absolute maximum possible velocity for any massive object, requiring energy inputs that approach infinite as you asymptotically approach light speed. At this velocity, relativistic effects become extreme. Time dilation would cause time aboard your spacecraft to pass much more slowly than time in the external universe. From your perspective, the journey to Andromeda might require only 25,000 subjective years rather than 2.5 million. This seems like an improvement until you realize that 25,000 years still exceeds the entire span of recorded human history. Everyone you know would be dead. Your civilization would have risen and fallen countless times. The human species might have evolved into something unrecognizable or gone extinct entirely. And when you arrive at Andromeda, you observe it as it exists 2.5 million years after the light left that you observe from Earth. The galaxy you aim for is not the galaxy you arrive at. Andromeda has continued evolving during your journey. Stars have been born and died. The galactic structure has rotated multiple times. If you want to communicate with Earth, your radio signals will take 2.5 million years to travel back, arriving when Earth's continents have drifted into completely new configurations. You have not achieved interstellar travel in any meaningful sense. You have achieved time travel into the future while moving through space. The destination and the origin no longer share a common present moment. You exist in temporal exile, separated from your origin not just by distance, but by time itself. And this is for Andromeda, the closest major galaxy. For more distant targets, the relativistic time dilation cannot compensate for the sheer distance involved. Even traveling at 99.9999% light speed, the journey to the Virgo cluster would require 500,000 subjective years aboard the spacecraft. You would need to build a generation ship sustaining populations for 500,000 years, or develop technology for suspending biological processes across timescales that exceed the entire span of mammalian evolution on Earth. The energy requirements alone make such journeys impossible with any conceivable technology. Accelerating a 1-ton spacecraft to 99.99% light speed requires energy approximately equal to the total energy output of our Sun for several weeks. Accelerating anything larger, say a habitat capable of sustaining a population, would require energy outputs that exceed what the entire human civilization has produced in its entire history by many orders of magnitude. Where do you get this energy? Nuclear fusion, even if perfected, cannot provide sufficient energy density. Matter-antimatter annihilation, the most efficient energy conversion process allowed by physics, would require carrying amounts of antimatter that equal substantial fractions of your spacecraft's mass. Antimatter that we currently cannot produce in meaningful quantities, cannot store without it annihilating with normal matter, and cannot contain in any vessel made of normal matter. You are trapped, not by lack of imagination, not by insufficient technology, but by the fundamental structure of space-time itself. The speed of light limit, the expansion of space, the sheer scale of cosmic distances, these are not engineering problems. They are physical constraints that cannot be overcome by better rockets or cleverer designs. The 2 trillion galaxies you catalog are tombstones, epitaphs written in light. You can observe them, measure them, study them, but you cannot reach them. The universe has built you a cage 93 billion light-years across and called it the observable universe. Everything beyond the bars exists in theory but remains forever inaccessible. Everything inside the cage is still too far away to touch within any time frame that matters to biological life or technological civilization. The catalog of galaxies is a catalog of the unreachable. Each entry represents a destination you will never visit. Each measurement describes a prison you will never escape. The next chapter reveals exactly what you will see if you attempt this impossible journey, and why every single photograph of distant galaxies is a lie about what actually exists. Every photograph of a distant galaxy is a lie. Not because astronomers fabricate data, not because telescopes malfunction, but because the act of observation across cosmic distances creates a fundamental distortion between what you see and what actually exists. You are not observing galaxies. You are observing light that left those galaxies billions of years ago. Fossils, echoes, ghosts burned into electromagnetic radiation. When the Hubble Space Telescope captured the extreme deep field image in 2012, astronomers pointed the telescope at a seemingly empty patch of sky and left the shutter open for the equivalent of 23 days of cumulative exposure time. The resulting image revealed approximately 5,500 galaxies in a region of space that, held at arm's length, would be covered by the head of a pin. Each galaxy in that image exists at a different distance, which means each exists at a different point in cosmic history. Some galaxies appear as they existed 1 billion years ago. Others show light from 5 billion years ago. The most distant objects in the frame emitted their light 13.2 billion years ago, when the universe was less than 4% of its current age. You are not looking at a single moment frozen in time. You are looking at a timeline of cosmic evolution stacked into 2 dimensions on your screen. The foreground galaxies are relatively recent. The background galaxies are ancient. And none of them exist in the state you observe. They have all continued evolving during the billions of years their light spent traveling through expanding space toward Earth. This temporal displacement creates a fundamental problem. When you observe a galaxy 10 billion light-years away, you see it as it existed 10 billion years ago. But that galaxy has continued evolving for 10 billion years since the light left. Stars have formed and died. Supernovae have exploded. The galaxy may have collided and merged with neighboring systems. The structure you observe may bear no resemblance to the galaxy's current state. And you can never know what that current state is. The information about the galaxy's present condition will not reach Earth for another 10 billion years. By the time that light arrives, another 10 billion years will have passed, and you will be observing the galaxy as it existed 10 billion years in your future, which by then will be the past. You are trapped in an observational prison where the present state of the universe is inaccessible. You can only observe the past. The farther you look, the deeper into history you see, until you reach the cosmic microwave background radiation. At 13.8 billion light-years distance, the afterglow of the Big Bang itself, beyond which you cannot see because the universe was opaque to light during its first 380,000 years. But the temporal displacement is only part of the distortion. The expansion of space itself warps the light as it travels. When light leaves a distant galaxy and begins its journey toward Earth, it travels through expanding space. As space expands, the wavelength of the light stretches. Blue light reddens. Red light shifts into infrared. Infrared shifts into microwave. The farther the galaxy, the more the light stretches, creating a phenomenon called cosmological redshift. Redshift is measured as the letter Z, which equals the change in wavelength divided by the original wavelength. A galaxy with redshift Z equals 1 has had its light stretched by a factor of 2. What was emitted as ultraviolet appears as visible light. What was emitted as visible light appears as near-infrared. The galaxy's entire spectrum shifts toward longer, redder wavelengths. The most distant galaxies observed by the James Webb Space Telescope have redshifts exceeding Z equals 13. Their light has been stretched by a factor of 14. Ultraviolet light emitted by hot young stars appears in the infrared when it reaches Earth. The galaxies themselves are invisible to optical telescopes. Only infrared instruments like Webb can detect them. This redshift encodes the galaxy's distance and the expansion history of space between the galaxy and Earth. Astronomers use redshift as a proxy for distance, with higher redshifts corresponding to greater distances and earlier cosmic epochs. But redshift also means that what you observe is radically different from what was emitted. Consider a galaxy at redshift Z equals 6, corresponding to a light travel time of 12.8 billion years. This galaxy emitted its light when the universe was only 900 million years old. The stars in this galaxy were young, hot, and predominantly blue. With surface temperatures exceeding 30,000 Kelvin, the galaxy blazed with ultraviolet radiation. But by the time the light reaches Earth, it has redshifted into the infrared. The ultraviolet has become visible blue light. The visible has become near-infrared. The near-infrared has become mid-infrared. You observe a galaxy that appears red and cool, not because it was red and cool, but because space has stretched its light during the journey. To reconstruct what the galaxy actually looked like when the light was emitted, astronomers must correct for redshift, shifting the observed spectrum back toward shorter wavelengths. This reveals the galaxy's true colors and properties at the time the light left. But this is a reconstruction, a calculation, not direct observation. And during the 12.8 billion years since the light departed, the galaxy has continued evolving. The hot blue stars that dominated when the light left have long since exploded as supernovae. Multiple generations of stars have been born and died. The galaxy may have merged with others, transforming from a small, irregular system into a massive elliptical. Or it may have been torn apart by gravitational interactions, its stars scattered across millions of light years. You cannot know. The information has not arrived, will not arrive for billions of years. And when it does arrive, you will be observing the galaxy as it existed billions of years in the future, which by then will be the past. This creates a maddening paradox. The observable universe contains 2 trillion galaxies, each frozen at a different point in its evolutionary history. The nearby galaxies show relatively recent states, only millions of years out of date. The distant galaxies show ancient states, billions of years old. But none of them show the present. If you could somehow travel faster than light and arrive at a distant galaxy instantaneously, what you found would bear no resemblance to what you observed from Earth. The galaxy would have aged billions of years. Its structure would be completely different. Stars you observed as bright blue giants would have exploded. Spiral arms would have rotated dozens of times. The galaxy might not even exist anymore if it merged with a larger neighbor. Every map of the universe is a map of the past arranged by distance. Every catalog of galaxies is a catalog of evolutionary states spanning cosmic history. You are not observing a universe that exists simultaneously. You are observing a 4-dimensional object, 3 spatial dimensions, plus time. Projected into 3 spatial dimensions on your telescopes and screens, the light travel time becomes a time machine pointed backward. The farther you look, the younger the universe appears. At 1 billion light-years distance, you observe the universe as it existed 1 billion years ago. Approximately 7% younger than it is now. At 7 billion light-years, you see the universe halfway back to the Big Bang. At 13.8 billion light-years, you approach the cosmic dawn, the epoch, when the first stars and galaxies formed. These early galaxies are radically different from modern systems. They are smaller, denser, more chaotic. Star formation rates are 10 to 100 times higher than in modern galaxies. Supermassive black holes at galactic centers are more active, consuming gas and radiating enormous amounts of energy as quasars. The intergalactic medium contains more gas and dust, with lower concentrations of heavy elements, because fewer stellar generations have synthesized and dispersed them. The universe at high redshift is a violent, turbulent place. Galaxy collisions are more common because galaxies are packed more densely in a smaller volume of space. The cosmic web of large-scale structure is still forming. Dark energy has not yet begun to dominate cosmic expansion, so the expansion rate is decelerating rather than accelerating. But this is not the universe you live in. This is the universe that existed billions of years ago. The modern universe has evolved, expanded, cooled, organized itself into the structure you observe nearby. The distant ancient galaxies have evolved into modern systems like the Milky Way. Or they have merged and disappeared. Or they have been torn apart by gravitational interactions. You will never observe these transformations directly. The timescales are too long. Galaxies evolve over billions of years. Human lifespans measure decades. Human civilizations measure thousands of years at most. You can observe snapshots at different evolutionary stages by looking at galaxies at different distances. But you cannot watch an individual galaxy evolve. Imagine trying to understand human development by observing 1 million different people of different ages at a single moment. You see infants, children, teenagers, adults, elderly people. From these snapshots, you can infer the general pattern of human development. But you cannot watch a single individual grow from infant to adult. The process is too slow. Galaxies are worse, much worse. The timescales involved are millions or billions of times longer than human lifespans. Entire civilizations could rise and fall in the time it takes a spiral arm to rotate once around a galactic center. Species could evolve from microbes to intelligence and back to extinction in the time it takes 2 galaxies to collide and merge. And you are trying to understand this process by observing distant galaxies billions of years out of date. The James Webb Space Telescope, launched in 2021, was specifically designed to observe the earliest galaxies at extreme redshifts. Its infrared instruments can detect light that has been stretched from ultraviolet and visible wavelengths into the infrared by redshifts exceeding Z equals 20. This corresponds to looking back to when the universe was only 200 million years old, less than 2% of its current age. Webb has already discovered galaxies that should not exist according to standard models. Massive systems with billions of stars formed when the universe was supposedly too young for such large structures to have assembled. The observations suggest that galaxy formation proceeded much more rapidly in the early universe than theories predict. Or perhaps dark matter behaves differently than models assume. Or perhaps our entire understanding of cosmic structure formation requires revision. But these are observations of the ancient universe, not the present universe. The galaxies Webb observes at high redshift have continued evolving. For 13+ billion years since the light left, they are not massive ancient galaxies anymore. They are modern systems like the Milky Way, if they survived and did not merge into even larger structures. You are observing a museum of cosmic history, with exhibits arranged by distance. The nearby exhibits are recent, the distant exhibits are ancient. And the present-day state of every exhibit is completely unknown and unknowable until billions of years pass and updated information arrives in the form of light that is currently in transit. This is not observation in any normal sense. This is archaeological excavation of light fossils. Every distant galaxy is a time capsule. Every photograph is a historical document. And every catalog is a chronology of cosmic evolution, frozen in the amber of light travel time. But even this distorted observation will not last forever. As dark energy continues to accelerate cosmic expansion, more and more galaxies will redshift beyond detectability. Their light will stretch into wavelengths so long that no instrument can detect them. They will fade from view, not because they stop emitting light, but because the light gets stretched into invisibility. In the far future, approximately 100 billion years from now, every galaxy outside the local group will have redshifted beyond the cosmic horizon. Future astronomers will observe a universe containing only the merged Milky galaxy, surrounded by empty darkness. They will have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence that 2 trillion other galaxies once filled the observable universe. They will think they live in a small, static island universe floating in infinite void. And they will be wrong, but they will have no way to know they are wrong because all the evidence will have literally expanded beyond their ability to observe it. You live in a privileged epoch when the universe remains partially visible, but you are observing a past that no longer exists, a history written in light, a record of states that have already transformed into something else, while the light traveled through expanding space toward your telescopes. Every galaxy in every catalog is dead. Not metaphorically dead, actually dead in the sense that the state you observe no longer exists. The stars have changed. The structure has evolved. The galaxy has merged or dispersed or transformed into something you cannot see, and will not see for billions of years. You are cataloging ghosts, arranging them by distance and redshift and evolutionary state, building models of cosmic history from archaeological fragments of light, and calling this science, calling this observation, calling this understanding. But the present state of the universe, the actual configuration of 2 trillion galaxies as they exist right now in some hypothetical cosmic reference frame, is completely inaccessible. You cannot observe it, cannot measure it, cannot know it. The speed of light and the expansion of space create an information barrier that makes the present unknowable. You can only know the past. And the farther you look, the older the past becomes until you reach the edge of the observable universe, where you observe light that is almost as old as time itself. This is the fundamental limitation of cosmic observation. You are not looking at the universe. You are looking at a light shadow of what the universe used to be, distorted by expansion, dimmed by distance, and obsolete by billions of years. The next chapter reveals what happened to all those ancient galaxies you observe at high redshift, and why the universe you see is already a graveyard. Galaxies die slowly, not in explosions, not in cataclysmic events that announce their passing. They fade gradually over billions of years as their fuel supplies exhaust. Their stars age into darkness, and their structures dissolve through gravitational interactions that scatter their components across intergalactic space. The death begins with star formation. Every galaxy contains a reservoir of gas and dust that collapses under gravity to form new stars. This process cannot continue indefinitely. Each generation of stars consumes gas and either locks it up in stellar remnants like white dwarfs, neutron stars, and black holes, or expels it from the galaxy entirely through supernova explosions and stellar winds. The Milky Way currently forms approximately 2 solar masses of new stars per year. At this rate, the galaxy will exhaust its gas reservoir in approximately 1 to 2 billion years. Star formation will gradually decline as less gas remains available for collapse. Eventually, the last star will ignite. After that, no new stars will ever form in the Milky Way. The galaxy will contain only the aging remnants of previous stellar generations. But 1 to 2 billion years is optimistic. The collision with Andromeda in approximately 4 billion years will dramatically alter both galaxies' star formation histories. When two gas-rich spiral galaxies collide, the gravitational interactions compress gas clouds and trigger intense bursts of star formation called starbursts. The Milky Way-Andromeda collision will consume much of both galaxies, remaining gas in a final frenzy of stellar birth. The starburst phase will last approximately 100 million to 1 billion years. During this period, star formation rates will increase by factors of 10 to 100. Compared to current levels, the merged galaxy will blaze with the light of billions of newly formed stars. Hot blue giants will dominate the luminosity. Supernova explosions will occur at rates far exceeding the current frequency. But this brightness is terminal. A dying star burns brightest just before it exhausts its fuel. The starburst consumes the galaxy's remaining gas reserves in a cosmic binge, leaving nothing for future generations. When the starburst ends, star formation will cease almost completely. The merged Milkomeda galaxy will enter a long, slow fade into darkness. The most massive stars formed during the starburst will explode as supernovae within 10 million years. Medium-mass stars like our Sun will last billions of years before swelling into red giants and ejecting their outer layers as planetary nebulae. Leaving behind white dwarf remnants, the smallest red dwarf stars will burn for 10 trillion years or more, far longer than the current age of the universe. As billions of years pass, the galaxy's stellar population will gradually shift toward lower masses and longer lifetimes. The brilliant blue giants will disappear first. Then the white and yellow main sequence stars. Eventually, only red dwarfs, white dwarfs, neutron stars, and black holes will remain. The galaxy will dim from its current brightness to a faint red glow, then to near invisibility as even the red dwarfs exhaust their fuel. Approximately 10 trillion years from now, the last red dwarf in Milkomeda will sputter and fade. At that point, the galaxy will contain no active fusion-burning stars. Only stellar remnants. White dwarfs slowly cooling toward absolute zero. Neutron stars radiating away their rotational energy. Black holes silently accreting whatever diffuse matter crosses their event horizons. This stellar graveyard will persist for an incomprehensibly long time. White dwarfs cool extremely slowly because they have no internal energy source. They radiate away their residual heat over trillions of years, gradually fading from white-hot to red to black as they approach the temperature of the cosmic microwave background. The faintest white dwarfs we observe today are approximately 10 billion years old and have cooled to temperatures around 4,000 Kelvin. They will require another 10 to 20 trillion years to cool to 3 Kelvin, matching the temperature of space itself. But even cooled white dwarfs do not last forever. Over timescales of 10 to the power of 32 years, protons may decay into lighter particles through processes predicted by grand unified theories of particle physics. If proton decay occurs, white dwarfs will gradually evaporate as the atomic nuclei comprising them disintegrate. The mass will radiate away as low-energy particles and radiation. The dwarf will slowly dissolve into the vacuum. Neutron stars face a similar fate. Even without proton decay, isolated neutron stars will eventually cool to the temperature of space and become invisible. If protons decay, Neutron stars will evaporate over timescales exceeding 10 to the power of 35 years, leaving behind only diffuse radiation and elementary particles. Black holes are the most stable stellar remnants, but even they are not eternal. Stephen Hawking predicted in 1974 that black holes emit thermal radiation through quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass extremely slowly. A solar mass black hole would take approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. The supermassive black hole at the center of Milkomeda, with a mass potentially exceeding 1 billion solar masses after consuming smaller black holes, during galaxy mergers, would require approximately 10 to the power of 100 years to evaporate. 10 to the power of 100 years. Written out, that is 1 followed by 100 zeros. The current age of the universe, 13.8 billion years, is utterly insignificant compared to this timescale. During these incomprehensible spans of time, galaxies themselves will gradually dissolve. Gravitational interactions between stars cause some to gain energy and others to lose it. Through a process called dynamical relaxation, stars that gain energy are ejected from the galaxy entirely, escaping into intergalactic space as rogue systems. Stars that lose energy spiral inward toward the galactic center, where they may eventually be consumed by the central black hole. Over timescales of 10 to the power of 19 to 10 to the power of 20 years, approximately 90% of the stars in a galaxy will be ejected. Through these gravitational interactions, the remaining 10% will collapse into a tight cluster around the central supermassive black hole. This cluster will gradually spiral inward and be consumed by the black hole over even longer timescales. Eventually, on timescales approaching 10 to the power of 100 years, the galaxy will have completely evaporated. Some stars will have been ejected into intergalactic space where they drift alone forever. Others will have fallen into the central black hole and been consumed. The stellar remnants that remain, cooling white dwarfs, cold neutron stars, evaporating black holes, will be scattered across volumes much larger than the original galaxy, separated by distances where gravitational interactions become negligible. At that point, the galaxy no longer exists as a coherent structure. It has dissolved into individual remnants drifting through expanding space, and this is the fate of every galaxy in the universe. Every spiral, every elliptical, every irregular system will eventually exhaust its gas, form its last stars, fade into darkness, and dissolve through gravitational evaporation. The 2 trillion galaxies you catalog are not permanent features of the cosmos. They are temporary condensations of matter that will persist for trillions of years, before dissipating back into the void. You observe them during a brief epoch when they shine brightly with the light of active star formation. But this epoch is fleeting. The universe will spend far more time in darkness than in light, and the darkness is already spreading. Elliptical galaxies, which account for approximately 30% of all galaxies in the observable universe, have already exhausted most of their gas supplies. These systems formed through major mergers of spiral galaxies, processes that consumed their gas in starbursts and expelled the remainder through supernova-driven winds and energy output from active galactic nuclei. Elliptical galaxies contain predominantly old red stars with ages exceeding 10 billion years. Star formation in these systems has essentially ceased. When you observe a massive elliptical galaxy, you are observing a galaxy that has already died in terms of active evolution. It will persist for trillions of years as its stars slowly age, but no new stars will form, no new planets will coalesce, no new opportunities for life will emerge. The galaxy is a mausoleum containing the slowly cooling remains of stars that formed billions of years ago. The fraction of elliptical galaxies increases toward the centers of rich galaxy clusters. In the Coma cluster, more than 80% of galaxies are ellipticals. This occurs because cluster environments are hostile to star formation. Galaxies moving through the hot intracluster medium experience ram pressure stripping that removes their gas. Galaxy collisions and mergers are more frequent in dense environments, triggering starbursts that consume remaining gas. Gravitational interactions with other cluster members can strip gas through tidal forces. Cluster galaxies die young. They exhaust their fuel and cease star formation billions of years before isolated field galaxies like the Milky Way. The universe's richest environments are already graveyards, filled with dead and dying galaxies that will never form new stars. But even isolated spirals face eventual starvation. The gas reservoir is finite. Each generation of stars reduces what remains. And the universe is not replenishing the supply. The Big Bang created primarily hydrogen and helium. Heavier elements are synthesized in stars and dispersed through supernovae. But this process does not create new hydrogen. It transforms existing material. And much of that material gets locked away in stellar remnants or expelled from galaxies entirely. The peak of cosmic star formation occurred approximately 10 billion years ago, when the universe was only 3.8 billion years old. At that epoch, galaxies were forming stars at rates approximately 10 times higher than today. The universe was brighter, more active, more alive. Since then, the cosmic star formation rate has declined steadily. Today's universe forms stars at only 10% the rate it did at peak. This decline will continue. 1 billion years from now, the cosmic star formation rate will be half of today's rate. 10 billion years from now, it will be negligible. 100 billion years from now, essentially no stars will form anywhere in the observable universe. The last stellar nurseries will have collapsed. The last protostars will have ignited, and then silence. The universe will enter an epoch called the degenerate era, lasting from approximately 10 trillion years to 10 to the power of 40 years after the Big Bang. During this era, no fusion-burning stars exist. Galaxies are invisible collections of stellar remnants drifting through darkness. The only light comes from the gradual cooling of white dwarfs, the occasional collision of brown dwarfs creating brief flares, and the accretion of matter onto black holes. After the degenerate era comes the black hole era, lasting from approximately 10 to the power of 40 years to 10 to the power of 100 years. During this epoch, all ordinary matter has either evaporated through proton decay or collapsed into black holes. The universe contains only black holes of various masses, slowly evaporating through Hawking radiation. The largest black holes, formed from galaxy clusters or even superclusters, dominate the mass budget, but even they slowly shrink, radiating away their mass as thermal particles and radiation. Finally, after 10 to the power of 100 years comes the dark era. The last black holes have evaporated. The universe contains only photons, neutrinos, electrons, positrons, and perhaps exotic particles predicted by theories beyond the standard model. These particles drift through space at temperatures approaching absolute zero. The universe expands forever, cooling forever, becoming more dilute forever. Nothing happens. Nothing can happen. The energy density is too low for any interesting physical processes to occur. This is the ultimate fate of your universe. Not a dramatic ending in fire or collapse. Just a slow, cold fade into darkness and emptiness that lasts forever. The 2 trillion galaxies you observe are temporary bright spots in a cosmos that will spend eternity in darkness. They exist during a cosmically brief window, from approximately 100 million years to 10 trillion years after the Big Bang, when conditions allow star formation and galactic structures to persist. You live near the beginning of this window. The universe is young, 13.8 billion years old, still actively forming stars, still containing galaxies with active evolution. But you can already see the death spreading. Already observe the elliptical galaxies that have exhausted their fuel. Already measured the declining cosmic star formation rate. The catalog of 2 trillion galaxies is a catalog of temporary luminous structures that will eventually fade into invisible remnants scattered across an expanding void. You cannot travel to them during their brief epoch of brightness. By the time any journey could reach them, they will have evolved beyond recognition or faded into darkness entirely. And your own galaxy will join them. The Milky Way will merge with Andromeda, form stars frantically for 1 billion years, exhaust its gas, fade into a collection of aging red dwarfs, eventually cool into a graveyard of white dwarfs, neutron stars, and black holes. Dissolve through gravitational evaporation, disappear. Everything dies, every star, every galaxy, every structure in the observable universe will eventually succumb to entropy. Quantum decay, or the relentless expansion of space, The light you see right now from 2 trillion galaxies represents a temporary anomaly in the history of a cosmos that will spend eternity in darkness. You are observing the universe during its brief childhood when it still glows with the light of star formation. Enjoy it while it lasts. The darkness is already spreading, already consuming the elliptical galaxies, already reducing star formation throughout the cosmos. Eventually, the darkness will consume everything, including you. The final chapter reveals why even the act of cataloging these doomed galaxies changes nothing about your cosmic imprisonment. Two trillion galaxies containing approximately 800,000 billion stars. Current estimates suggest at least 1 planet per star, giving approximately 800,000 billion planets in the observable universe. Rocky planets number in the hundreds of billions. Planets in habitable zones where liquid water can exist number in the tens of billions. Somewhere in that census, life must exist. The numbers make any other conclusion statistically absurd. The chemical building blocks for life are common throughout the universe. Carbon, hydrogen, oxygen, nitrogen. The elements comprising organic molecules rank among the most abundant elements in existence. Water molecules pervade interstellar space. Complex organic compounds, including amino acids, form naturally in molecular clouds and have been detected in comets and asteroids. The conditions that allowed life to emerge on Earth are not unique. Our planet orbits a typical main sequence star at a distance where temperatures permit liquid water. The Sun is one of approximately 400 billion stars in the Milky Way. Hundreds of billions of those stars are similar to the Sun in mass, temperature, and lifetime. Many possess rocky planets in their habitable zones. The Kepler Space Telescope, which operated from 2009 to 2018, discovered thousands of exoplanets and provided statistical data on planetary occurrence rates. Analysis of Kepler data suggests that approximately 20 to 50% of Sun-like stars host planets of roughly Earth's size in the habitable zone. Apply this to 400 billion stars in the Milky Way, and you get 40 to 200 billion potentially habitable worlds in our galaxy alone. Multiply by 2 trillion galaxies, and the number of potentially habitable planets in the observable universe exceeds 10 to the power of 22. 10 billion trillion potentially habitable worlds. 10 billion trillion locations where liquid water might exist, where organic chemistry might operate, where life might emerge. And yet we detect nothing. No signals, no evidence, no indication that any other intelligence exists anywhere in the observable universe. This is the Fermi paradox, articulated by physicist Enrico Fermi in 1950 during a casual lunch conversation. Fermi asked a simple question that has haunted astronomers ever since. Where is everybody? Given the vast number of potentially habitable worlds and the billions of years available for intelligent life to evolve, the galaxy should be teeming with civilizations. Some should be millions or billions of years older than humanity. They should have developed interstellar travel, colonized multiple star systems, built megastructures visible across light years. We should detect their radio transmissions, their waste heat, their artificial structures modifying planetary systems. And harnessing stellar energy, we detect nothing. The search for extraterrestrial intelligence, abbreviated SETI, has been monitoring the skies for artificial radio signals since 1960. Thousands of hours of telescope time dedicated to listening for patterns that might indicate technological origin. Sophisticated algorithms scanning millions of frequency channels simultaneously, searching for narrow-band signals or repeated patterns that natural processes cannot produce. 65 years of listening, billions of frequency channels monitored, thousands of star systems examined, and the result is silence. Perfect, absolute, crushing silence. The universe broadcasts noise, thermal radiation from stars, synchrotron emission from magnetic fields, bursts from pulsars and magnetars. But no artificial signals, no encoded messages, no indication that anyone else is transmitting. Perhaps we are searching incorrectly. Radio waves are our technology, developed in the late 19th and early 20th centuries. Advanced civilizations millions of years beyond us might use communication methods we cannot detect. Neutrino beams, gravitational wave modulation, quantum entanglement channels. Technologies so far beyond our current capabilities that we would not recognize them even if they passed directly through our detectors. But this explanation requires that every civilization in the galaxy abandoned radio technology so quickly that we never detect their radio era. That every species advanced to exotic communication methods before spreading beyond their home system. That none are currently in their radio broadcasting phase. Despite the galaxy's billions of stars, perhaps civilizations are rare. The jump from chemistry to biology might require conditions far more specific than we realize. Or biology to intelligence requires evolutionary paths so improbable that Earth represents a statistical fluke. Or intelligence to technological civilization requires social and cognitive developments that rarely occur. Each step filters the population. Until only a handful of technological civilizations exist per galaxy, separated by distances and times that prevent contact. This is the rare Earth hypothesis. It suggests that while simple microbial life might be common, complex multicellular life requires an improbable combination of factors. A planet in the habitable zone around a stable star. A large moon to stabilize axial tilt. A magnetic field to shield against radiation. Plate tectonics to regulate atmospheric composition. A gas giant in the outer system to deflect comets and asteroids. Each requirement reduces the population of suitable worlds. Intelligence might be even rarer. On Earth, intelligence evolved only once in 4 billion years of life. Billions of species have existed. Only one developed technology capable of leaving the planet. Perhaps intelligence is not inevitable. Perhaps it is an accident, a random mutation that happened to provide survival advantages in one particular lineage at one particular time. Or perhaps the Great Filter exists. This hypothesis suggests that somewhere between simple chemistry and galaxy-spanning civilization lies a barrier that almost no species crosses. A filter so severe that it reduces populations from billions of potential sites to effectively 0 observable civilizations. The filter might lie behind us. Perhaps the jump from non-life to life is extraordinarily difficult, requiring conditions so specific that Earth might be the only planet in the observable universe where it occurred. Or perhaps the jump from prokaryotic to eukaryotic cells, which took 2 billion years on Earth, represents a filter so difficult that most biospheres never progress beyond bacterial mats. Or the filter might lie ahead. Perhaps every technological civilization discovers nuclear weapons and destroys itself, or develops artificial intelligence that eliminates its creators, or depletes its planetary resources and collapses into extinction before achieving interstellar capability, or encounters some unknown technological danger that we have not yet discovered, but will inevitably face. If the filter lies ahead, we are in danger. Every year we survive without self-destructing moves us closer to whatever catastrophe. Eliminated every other species that reached our level. The silence of the galaxy becomes a warning. They were here, they developed technology, they disappeared, and whatever destroyed them awaits us as well. But perhaps the explanation is simpler and more terrible. Perhaps civilizations exist but are separated by such vast distances that contact is physically impossible. The speed of light limit ensures that even neighboring star systems are years apart for light-speed communication and centuries apart for physical travel. Galaxies are millions to billions of light-years distant. Even if thousands of civilizations exist in each galaxy, they remain forever isolated. Unable to communicate or interact across intergalactic voids. This is the dark forest hypothesis, popularized by Chinese science fiction author Liu Qixin. It suggests that civilizations remain silent deliberately because revealing your existence is dangerous. The universe is a dark forest where civilizations are hunters. Moving silently through the trees, the first one to make noise gets destroyed. Every species capable of reaching the stars is also capable of destroying other species. Contact with aliens might mean extinction, so everyone stays quiet, everyone hides, everyone listens but never broadcasts. If true, The silence is protection. SETI will never detect signals because no one transmits. Our own radio leakage from television, radar, and communication satellites has been radiating into space since the 1930s, potentially revealing our presence to anyone listening within 95 light-years. We have exposed ourselves. If predators exist, they now know we are here. But perhaps no one is listening. Perhaps the galaxy is sterile. Earth is alone. 4 billion years of evolution produced one technological species on one planet, and that is the only instance in the entire observable universe. We are unique, isolated. The only consciousness that will ever emerge from lifeless matter in this cosmic epoch. The numbers seem to argue against this. 800,000 billion planets. Billions of years for life to evolve. Chemistry that operates identically everywhere in the universe. How can Earth be unique? But unique does not mean impossible, only improbable. If the probability of life emerging is sufficiently low, say 1 in 10 to the power of 25, then Earth might be the only inhabited world in the observable universe. The only location where chemistry became biology, became intelligence. Everyone else is rocks and ice and empty skies. This is the loneliest possible answer to the Fermi paradox. Not that we are in danger, not that others are hiding, not that we are searching incorrectly, but that we are alone. Actually, truly, completely alone in a universe of 2 trillion galaxies containing nothing but dead matter and deterministic physics. Your species evolved on one planet around one star. You developed intelligence, language, technology. You built telescopes and discovered that the universe is vast beyond comprehension. You cataloged 2 trillion galaxies, 800,000 billion stars, 10 billion trillion potentially habitable worlds. And you are the only ones looking. The only ones asking questions. The only ones who care. Everything else is dead rock orbiting dead stars. Or dead stars becoming white dwarfs and neutron stars and black holes. Or dark matter and dark energy and empty space expanding forever. No other minds, no other civilizations, no one to contact, no one to meet, no one to share your discoveries with. You are the universe becoming aware of itself, and that awareness exists in only one location across 93 billion light-years. Even if other civilizations exist, they might as well not. The distances ensure you will never communicate. Never meet, never know if they are out there. You can broadcast signals and wait decades or centuries for responses that will never come. You can listen for signals and hear only noise. You can build better telescopes and discover more galaxies, but discovery changes nothing about isolation. The catalog of 2 trillion galaxies becomes a catalog of cosmic loneliness. Each entry represents a vast collection of stars and planets that you will never visit, where life might or might not exist, where civilizations might or might not have arisen and fallen, and where you have no way to ever determine which is true. The galaxies are there, blazing across the cosmos, completely inaccessible, completely unknowable beyond the ancient light that reaches your telescopes. You have mapped the observable universe, measured its size, counted its galaxies, calculated its mass, determined its age and expansion rate and ultimate fate. You understand the physics that governs cosmic evolution from the Big Bang to the heat death. You can predict what will happen trillions of years in the future when the last stars fade. And none of that knowledge changes your situation. You are trapped on one planet, around one star, in one galaxy that will eventually collide with Andromeda and fade into darkness. You can observe 2 trillion other galaxies through telescopes. You can catalog them and classify them and measure their properties. But you cannot reach them, cannot communicate with them, cannot affect them or be affected by them in any meaningful way. The observable universe is your cage. 93 billion light-years across, containing 2 trillion galaxies, 800,000 billion stars. And you are locked inside, unable to exit, unable to explore, able only to look and measure and understand precisely how isolated you are. This is the ultimate cosmic horror. Not that the universe is hostile, not that dangers lurk in the darkness waiting to destroy you, but that the universe is empty and vast and you are alone in it, forever separated from everything else by distances that physics itself makes insurmountable. You can see infinity, you just cannot touch it. The 2 trillion galaxies you catalog exist as museum exhibits behind glass. You can observe them, photograph them, study them, but you cannot interact with them. They are separated from you not by barriers that engineering might overcome, but by the fundamental structure of space-time. The speed of light is not fast enough. The expansion of space is too rapid, the distances are too vast. And your species' lifetime is too short. Even if you survive for 1,000,000 years and develop technology beyond current imagination, you will not escape this cage. You will not visit other galaxies. You will not contact other civilizations if they exist. You will remain forever in your cosmic neighborhood, observing the unreachable through telescopes, knowing exactly what exists and exactly why you cannot access it. The act of cataloging changes nothing. Discovering 2 trillion galaxies instead of 200 billion does not make them more accessible. It makes the isolation more extreme. You now know that 2 trillion separate collections of stars and planets exist beyond your reach. 2 trillion destinations you will never visit. 2 trillion potential homes for life that you will never meet. You have completed the census of your cosmic prison, measured its extent, mapped its contents, calculated its future evolution, and confirmed that the bars are permanent, built from the laws of physics themselves, unbreakable by any technology that does not violate the fundamental structure of reality. This is what you have achieved by cataloging 2 trillion galaxies. You have measured the exact dimensions of your eternal isolation. Right now, as you sit absorbing these facts, photons from 2 trillion galaxies are rushing through space toward Earth. Some left their sources yesterday, some left millions of years ago, some left billions of years ago, traveling through expanding space while your planet formed. While life evolved, while your species emerged from the savannah and built telescopes to capture their arrival. These photons carry information, wavelengths that encode temperature and composition, redshifts that reveal distance and cosmic history, patterns that show galactic structure and evolution. You collect this information, process it, transform it into images and catalogs and scientific papers. And none of it changes the fundamental truth. You are here. They are there. The space between is vast and expanding. The speed of light is finite. The journey times are impossible. You will never cross these distances. Never visit these galaxies, never know what exists there beyond the ancient light that happens to reach your location. The universe has given you eyes to see infinity and legs that cannot carry you beyond your own solar system. You can measure cosmic distances in light years and gigaparsecs. You can catalog structures spanning hundreds of millions of light years. You can observe the universe's evolution from the Big Bang to the present. But you remain trapped in one location, watching through telescopes as 2 trillion galaxies drift forever beyond your reach, separated by voids that transform travel into fantasy and contact into impossibility. This is your cosmic inheritance. A universe of staggering scale filled with structures you can observe but never access. 2 trillion galaxies, 800,000 billion stars, 10 billion trillion potentially habitable worlds, all unreachable, all inaccessible, all separated from you by distances that make the concept of journey meaningless. You have journeyed to every galaxy in the universe by looking through telescopes. You have seen them all, cataloged them all, measured them all, and confirmed that you will never physically reach even one. The journey is complete, the catalog is finished, the isolation is absolute. If this revelation has changed how you see your place in the cosmos, hit that like button and subscribe. Because understanding your cosmic imprisonment is the first step toward accepting that some cages have no exit. The universe is watching, but no one is watching back.